Hi Jaideep, I'm Chandramali, the TECO for this course. So this week it's mainly about putting different particles into boxes or energy levels. So before I have prepared few questions. Before going into that, what doubts do you have from assignments or anything related to the course this week?
Yes, sir, I have some doubt.
Okay,
Question number 257 9 10
right. Two.
in
Okay.
quiz section.
Yes, yes. Two, then five,
7
and
9
then
10.
seven, nine, 10. Okay, fine. I have prepared some of the questions related to that, so we can discuss that as well. Ninth question is quite easy only, but then I have not prepared that. Okay, I'll tell you. Okay, fine. So that case, all right. So let's start the discussion then. First, let me share my screen. Yeah. Just give me a moment. There is no problem related to you. Okay, let's see. Screen sharing. Yeah. Are you able to see my screen? Are you able to see my screen, Jadid?
Yes, sir.
Okay, fine. So let's get started, okay? So, see, whatever questions you have asked, um, I'll not tell the exact answers, but there are some problems from this which are related to that, okay? So, from that, you will be able to solve the questions, all the assignment problems. Fine? Okay, so let's get started. So, first question is about how you can put 15 indistinguishable lattice-side gas particles distributed in 17 sites. So, how do we go about this? All right. So before going into these things, no, let's just quickly revise few conditions, okay? So that it's easier for you. Okay, tell me what are the conditions, okay? So sir taught in classes like, balls and boxes are particles and energy levels. So there are conditions like distinguishable, indistinguishable, something like that, okay? So now let's just consider simple things, okay? Like first, I'll write it as balls and boxes so that it's like quite simple. You have to tell me all the formulas, okay? Number of possibilities. Number of possibilities. I'll write it here. Now, what I'll do is I'll write distinguishable and indistinguishable. Let me create some more space here. Balls. Okay. So now let's say first balls are distinguishable. Balls are distinguishable. Balls are distinguishable and this is indistinguishable. I'll just write indistinct. Okay. Or else I'll just put distinct. Let's put distinct and indistinct. Okay. So now tell me the formula for this. Yes, Jaydeep.
Yes, sir.
Okay, first simple case. Okay, both are distinct. That means there are different boxes, there are different balls. So now let's say I'll keep this as N. I'll keep this as N, this as R. Huh. Now you tell me.
Probability 1.
Not possibilities. Number of ways it can be done. Probability is one, I accept. Total probability. But number of ways you can do it.
1 way.
See, okay. Let's consider two boxes or two coin tosses, and then let's say 100 times you flip a coin. So what is the number of possibilities? Only two boxes, no. So 2 power 100, no.
Yes, sir.
So this is R power n. This is the number of possibilities. Okay, when both are distinct. Fine.
Yes, sir.
Okay. So now next one is distinct and another is indistinct. So that condition will come to. Or else first maybe both are indistinct. Okay. We'll just say both are indistinct. Doesn't matter. We do not know, we cannot distinguish between the boxes and particles. So then all that we do is, what is the formula here? There's something called partition of integer. Okay. Did you listen to the lecture?
Yes, sir.
So you saw that partition of integer, right?
Yes, sir.
So it is P of, wait, somebody came. Yeah. Okay. So partition of integer is P power, sorry, P n. So number of balls. So basically we want to see how many ways we can separate these balls into. So that's the simple idea. So these are the two cases. Now we have one is distinct, another is indistinct. So that is the case we are coming to. All right. Hmm? Now let's say
Okay.
the hello. Did you tell something? Okay. All right. So let's say one is let's say balls are distinct and boxes are indistinct. Fine. Now you tell me how we go about this. And then another case is indistinct, and then this is distinct. So these are the four cases that we are going to see in all our problems this week. So it's quite simple. Once you know these formulas, then it's quite simple. Now balls are distinct, boxes are indistinct, but there is some condition, like this is the number of boxes, or this is the total number of energy levels, something like that will be there. Okay. So then how will you go about it? That's the thing. Do you remember this formula that's taught in class? N plus R minus 1 or R
N
plus.
plus R minus 1, C N minus 1.
Yes. Okay. So this one, last one, then what is the answer?
NPR,
Not PR. You're there, not PR.
NCR.
NCR. Okay.
Oh, yeah, yes. NCR.
Sorry. Not NCR, RCN. I just changed the number now. So number of boxes by number of, uh, I mean total number of boxes, and then the way you are arranging these particles. Okay. Or whichever is greater. That's way. Fine.
Yes, sir.
Fine. So that's all we need to figure out now. So these are the formulas that you remember. That's enough, more than enough. So now, first question. So there are 15 indistinguishable gas particles. That is, so basically it's like N is 15. Basically 15 particles are there. All right, number of particles. So you can consider them to be like balls. And then you have number of sides is equal to R is 17. So you can consider them to be like um, number of boxes. So now what is the number of possibilities?
RCN.
Ah, yeah. So simple. What is R? 17, C 15. Correct. So
Yes,
now
sir.
what's the formula? 17 factorial divided by 15 factorial and 2 factorial. Correct. So how much is this? 17. So this will be 16 into 17 divided by 2 factorial, which is 1 into 2. Let's just do it. 18 sevens are 18 17. How much is that? 8 sevens are 56. 5 136. Okay. So that is the number of possibilities. Fine. Simple now. Any doubts, JD?
No, sir.
All right. So basically, once you understand these conditions, and then you see each question, and then figure out what exactly fits into this one of these, then you're set. Then data is just simple application of formula. Fine. Okay. So next question. If there are five distinguishable degenerate energy levels, okay, all energy levels, the what do you mean? The all in all energy levels, the energies are equal. Okay. And then 12 distinguishable particles are there. Fine. In how many ways can be? Okay. Huh. So actually we dealt with the problem of this kind last week. Can you tell me how we solve this? You read the question and tell me how we solve this. Okay. Remember last week we did something like this and we solved it using simple formula. Yes, JD. Okay, we solved a problem like this last week. You tell me how we solved. First thing is all energy levels have equal energy. So that means there is no bias there. So basically it's like a flat potential. We don't have to worry about energy levels. All energy levels are equally probable. That's the thing about degenerate energy levels. Okay. So now there are totally 5 degenerate energy levels. So that means R is equal to 5. And then there are 12 particles totally. Fine. They are all distinguishable. Now, so they are asking us that what are the number of ways the this such a system can be arranged if N1 first energy level is 6. 6 particles are there in the first energy level, and then in second energy level there are 3 particles. Third energy level there are 2 particles. Fourth energy level there is just 1 particle, and fifth energy level there are no particles. So these are the 5 energy levels. These are the number of particles, and they're asking us what are the number of ways this can be done. Okay. Since all the particles are distinguishable, there is a finite number of ways this can be done and it could be large. Last week we did a problem of similar kind. Do you remember? There's something called multinomial expansion.
Yes, sir.
Huh. So how did we do it? What's the formula for that? You have total number of particles. Huh. Okay. Let
Mm,
me write it. Do you
yeah.
remember how we did
Yes,
that?
sir. Yes,
How
sir.
12,
Uh,
then
12 and under the 6, 3, 2, 1, 0.
yeah, you remember that. So now what is the formula for this?
12 factorial divided
Ah,
by
yes,
6 factorial, 3 factorial, 2 factorial, 1 factorial, and
good.
0
That's
factorial.
all. Yeah, okay. That's all. Simple, right? So now how do we solve this? I'll just create some space here. So how do we solve this? 12 factorial, it will go. I'll just cancel this 12 and 6 factorial. So remaining will be 7 into 8 into 9 into 10 into 11 into 12 divided by 3 into 2 into 2, remaining 1 only. So I'll just leave that out. So how much is this? 13 into 2 into 2, 4. So everything is 12. Just cancel that. So we need to figure out the remaining thing. Okay. How much is this? How much is this value? 99 to 10 to 56. How much is this, Jadip? Round up.
55440.
How much? 55440. Okay. Yeah. So that is the number of possibilities. You see, because the particles are distinguishable, see the huge number of possibilities that are available. Okay.
Yes,
You
sir.
got the idea, right?
Yes, sir.
Okay. Now, third question is also similar. So you read the question and tell me how we can solve this. You think about it and then tell me. I'll give you a few minutes.
N plus R minus 1 C N minus 1. This formula.
Not exactly. You don't have to do that. There's a simpler way. Very easy way actually. You think actually we can do like that also, but there's a simpler way. You just this is the main clue, okay? You read this line and then think about it. What is the way that we can do it? Okay? What does this mean? You tell me that. So there are totally 5 molecules, and then energy is 5E. So they're telling there is a configuration in which energy is distributed evenly over all the molecules. So that means each particle has the same amount of energy. So there are 5 particles. There is 5 E amount of energy. So if all particles should have the same amount of energy, what is the energy of each particle now? You tell me that.
1.
Correct. So each particle will have one. So that means what? All the particles, all five particles will occupy J is equal to which energy level? 0, 1 or 2 or 3?
Yes, sir.
Which one? Which one? Which one will it occupy? So let's say this. Okay, I'll just draw. So there'll be more energy levels. Okay, here energy, I'll just write this is energy level 0 is equal to 0. Energy level 1 is equal to what? J into E, right? So J is 1, so it will be E. Energy level 2 is equal to 2E,
E.
correct? So like that, 3E. So now, if all the particles occupy this particular state, okay, just a minute. Give me a moment. I think it's just buffering. So basically, if all the particles occupy the same energy level, so all five particles should be in just this one energy level, right? Energy level 1. It will not, none of the particles in any of the other states, correct?
Yes, sir. Oh,
Huh. So, okay, just give me a moment. Why is this happening? Suddenly my document is getting hanged. Okay. So, suddenly everything hanged. Things coming now. Okay. Huh. So all the particles are in energy level 1. So that means what? So let's consider there are 5 energy levels. Fine. So then it's again like a multinomial distribution, right? 5 particles with energy level 0, it is 0. Then energy level 1, there are going to be 5 particles because all the 5 energy particles will have the same energy 1. Correct. So everything else will be 0. Fine, Jadip? Do you understand this point? Hello?
yes, sir. Yes.
If you have some doubt, you ask me, okay? So this is how this is going to be. So this is just 5 factorial divided by 5 factorial, which is just 1, correct? So there's just one way this can happen. So it's a simple thing. Fine? Did you understand?
Yes, sir.
Okay. Now you tell me the number of microstates in that. So now whatever you told above question. So this is the number of way it can happen. Okay. Now number of, or else I'll just put number of way. Okay. Number of ways, correct. That is the correct number of ways. Now number of microstates, what you told on formula, right? What is the formula? We'll use that formula now. What formula did it tell, Jiri?
N plus R minus 1.
Correct.
C
N
N
plus R
minus
minus 1, C, N minus 1.
1.
Now,
Yeah.
what is N here? How many particles?
5.
Ah. What is R? How many energy levels?
1.
No, 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 no. See here, see here. 5E, no? 5E. So
Total
what is the
energy.
total? Huh?
Total energy is 5.
So that's what we have to put here. Okay.
Oh,
Total energy available for all the five particles together. That is what you have to put in R. Okay.
okay, sir.
So this is going to be 9C4. So how much is that? So that is 9 factorial divided by 5 factorial divided by 4 factorial. Let's just divide 5
1
into
to
all.
6.
Okay. 1 to 6. Huh? 1 to 3 into 4. All right. So that is 1 to 6. Fine. So that is the number of possible microstates. Did you ask anything? Fine. Now you think about this problem and tell me which formula to use. This is direct application of formula.
N plus R minus 1 C N minus 1.
No. See what are there? Both are what?
5 indistinguishable.
Both are indistinguishable, right?
Yes, sir.
Box also distinguishable, particle also indistinguishable. Both are indistinguishable. Then what do you use?
7 indistinguishable part for
Both are indistinguishable. Then what do you use? You see here? What do
E
you use?
N.
Partition of integer, right?
Yeah.
Okay. So we use both are indistinguishable. Both indistinguishable. And n is equal to 5. So number of possible ways. Number of ways is equal to what? Partition of integer 5. So how do we calculate partition of integer? Just a
N
simple.
factorial.
No. So see, we generally calculate it like this. Number of ways you can divide 5 into 1 plus number of ways you can divide 5 into 2. Okay. See, P, this means number of ways you can divide 5 into 1. There is only one way you can do that. Okay. Similarly, okay. Number of ways you can divide 5 into 2. That you have to check. Then number of ways you can divide 5 into 3. We have to check. Plus number of ways we can divide 5 into 4. That also we have to check. Plus number of ways you can divide 5 into 5. Alright. I'll tell you how to do. So now let's consider each possibility. Fine. So what is P in 5 of 1? You're just, see, basically you're dividing 5 into just one part. So how can you divide that? There's only one way, na? All 5 will be together. Correct. There's only one part here. Okay. Now we need to divide 5 into two parts. What are the what are the ways in which you can divide 5 into two parts? There are two ways. How can we divide 5 into 2? 4 plus 1 is 5, right? Huh?
Yes, sir. And
Huh.
2 23.
Then 2 and 3. Correct. So 2 comma 3. Fine. Sorry. Just put this bracket. So this is one way. This is two ways. Okay. Then how can we divide 5 into 3? Three parts. Now you tell me this. What are the ways in which we can divide? 1, 2, 2. Okay. Then any other way? 1 comma 1 comma 3. Fine.
Yes, sir.
Two ways. All right. Then p is 5 comma 4. We have to divide it into 4 parts. There is only one way we can do that. 1 comma 1 comma 1 comma 2. Fine. Again, just one way. Just one way. Sorry, mosquito. Then you have to divide 5 into 5 parts. How can we do that? Tell me.
1 comma 1 comma 1.
Only one way, right? So totally how many ways? 1 plus 2 plus 2 plus 1 plus 1, 7 ways. Correct?
Yes, sir.
So the answer is 7 now. So since this is a small integer, 5, we can do it manually. But we cannot do this manually for all the integers, because as the number of integers increases, the number of possible ways partition of integer will increase exponentially. So we cannot use this manual method all the time. All right. So what we'll do is I'll just quickly show you how to do it. Partition of integers calculator. Ah, integer partition. Calculator. Integer. All right. So let me just share just change the screen to something else. Tab. Alpha. Okay. So there is a website called Wolfram Alpha or Mathematica. If you go there, you will have this partition calculator. All right. Can you see this, Jadip?
Yes, sir.
Now you can just put any number over here. Let's say we'll put 5 and we should get 7. Correct? We'll just submit. Does not change for you. I have to change present something else. For now, I'll just present the entire screen so that it's easy for you. Huh. You can see now. So when I'll just close it, do it again. So I'm just submitting it now. New tab will pop up where they are calculating the partitions of integer 5, and you see number of partitions is equal to 7. Okay.
Yes, sir.
You saw we can give some high integer number also. Let's say I'll just give 15. If I give 15, there are 176 partitions. And let's say I give 150. It will just increase exponentially. See, it became some 2 lakh partitions, number of partitions. So it just keeps increasing as you increase the number. Fine. You got the idea?
Yes, sir.
Okay. Wait, let me just stop presenting this. Huh. I have this mosquito, sorry. Okay, now let me share this. So this is how you can quickly calculate using this Wolfram Alpha. So you do that for assignments. Don't sit and do all these big calculations, sitting and checking all possibilities. No need for that. Just check in Wolfram Alpha, it will be fine. All right. So now, okay, now you see this problem and let me know how we can solve it. Actually, the total number of waves is straightforward. How many distributions you will have to think and tell me. Just think about it and tell me.
Five distribution are possible.
Sorry, how many? Okay, so first, let's consider this. There are five particles, okay? So basically, you'll have to distribute them among energy levels. So what are the total number of ways you can divide five particles? You tell me that. Total number of possible distributions. We just did that problem. Basically, we'll have to divide those things, no? Just think about this and tell me.
Seven ways possible to distribution.
Okay. How are you telling that?
Yes, question.
Previous question, what are we telling? Okay, previous question we are telling like this. So then, hmm, tell me.
We can distribute seven ways.
Ah, okay, then. But is that correct? Tell me that. Think about it. Total energy should be 5, okay? You just think about it and tell me then. Really, really sorry. 2 minutes. Yes, you tell me. You think about it and tell me, okay? Just take your time, think about it, tell me.
120 ways.
No, no, base is fine. That is okay. That is next. That is next. Okay. But before that, see, there are 7 ways. I accept that. But are all the 7 ways possible when we think about 7 energy levels? So what are the 7 ways? Let's just wait. Total number of possible distributions. Let's say we have five. This is one. Then 4, 1. We are just partitioning. Okay. Huh. Wait, did somebody come? All right. So this is there. Then we can partition it like this. Correct? Then anything any other way? 1, 2, 2. Then what are the other ways? 1, 1, 3. Correct? Then what are the other ways? 1, 1, 1, 2. Then 1, 1, 1, 1. All right. Fine. So now let's think. First, let's see. Always you have to check if this can be possible. There are five. Let's consider there are 5 energy levels now. Okay, there are 5 energy levels. Sorry, not five, 6. One can be zero, right? Can be energy level can be. So I'll just put 0, 1, 2, 3, 4, 5. Okay, okay, Jadip. So now first tell me, all five particles are together. Is that possible? We need 5e energy. This is 1e, this is 2e, this is 3e, 4e, 5e. Is this possible?
Yes, sir.
All uh, all five together, and then satisfy the condition that 5e is possible. Is it possible? Yes, right? You can put all five here in 1e, and then total energy will be
5.
together, and you're in the same place. Correct?
Yeah,
So this is possible. Fine.
yeah.
Okay. Now tell me whether this is so like this. Think and tell me whether next one is possible. Is it
4e
possible? Uh-huh.
plus
Yes, yes. Should be 5. Total energy should be 5.
4e plus 1e.
Four, no, 5 particles. 5 particles. Think about it. Okay, you can put
No
four
others.
particles with 0 and then one particle with 5. Is this possible? So then also energy will be 5. Correct?
Yeah.
Ah,
Then we will use one
ah.
particle. No,
One
no, no,
particle
no.
will be at 5e. Okay. So this
Yeah.
is also possible. So next is 3 and 2. Is there a combination that will make the energies possible? Three
If we
particles.
use 3 plus 1e, মানে one e, one particle in 1e and 4 particle in 4e. Then we total particle is 5e.
How?
Right?
If you put 4 particles here,
Yeah,
what is the energy? 1 4e, then 8e, then 12e, 16e. That's more than 5e, na?
yeah.
That is not possible. Now think about 3 and 2. Is there a combination that will make it possible?
2 to 1.
2, 2, 1. Right. You need to put 3 particles where?
Yeah. We
I don't.
we use 2e in 2e section 2 particles and one is x and one particles. Then
No,
2
you
plus
see,
2.
no, you see 3 and 2. I'm talking about this 3 and 2. You need to have three
is
particles in one of these and two particle in one of another level. So actually this is not possible. Okay. So then 1, 2, 2.
No, it's not possible. If we input a particle to
It is
2,
possible, no? You put two particles here, two particles here. No, one particle here.
yeah,
One particle here and then two
I
particle
have
here.
some
So
0.
what is the energy now? 2
Total
plus
5.
2, 4 plus 1, 5. 5e. Okay.
Yeah,
So this is also possible. 1, 1, 3.
one,
Is that
3.
possible? 1, 1, 3 is possible?
Yeah, possible.
Plus, huh, huh,
1 and
1 and
3
3 and
and
2.
2. Yeah,
Okay, this is also possible. Correct. Then this one, 1, 1, 2.
1, 1. No,
Hmm. Let's think about it.
not possible.
Okay, let's think once. 2, yes.
Oh, now I am understand.
So this is again 1, 1, 1. That also is not possible. 1, 1, 1 can now is not also not possible. This is not possible. Then what about this? Is that possible? 1, 1, 1, 2. If you put 2 here, 1, 1, 1, 6e won't be possible. Yes, this is also not possible. Then, is this possible? 3. No, that is also not possible. Okay. So, I mean, this is how we need to think if total energy is involved. Okay. You got the idea?
Yes, sir.
Huh. So now,
Step.
okay. So now this is total number of possible ways is 4 then, only 4. But then if you want, so this is these many types of distributions are possible now, but total number of ways, w total, that you, what formula did you tell? That only we have to use. N is equal to, you tell the formula here. N is equal to what? N is equal to 5 and R is equal to 5, correct?
Yeah,
So what's the formula? What is the formula?
and in here R to the power. Yeah, N to the
N w total is equal to N plus R minus 1 C N minus 1, correct? So it will be 9C4. And how much is that? We already did that. 4 factorial, 5 factorial. How much is the value, Jadip? We already did this. 126, right? We did this before, remember? 6 into 7 into 8 into 9. You only told me 126 answer.
Yes, sir.
So this gone. This is 2. 14 into 9, which is 126. Correct. Okay. Okay. Now we'll do the next question. Now you tell me, how do we solve this?
Only one way. First question.
Only one way. Okay, why?
Because in question there can be only one quanta per particle, but here particle number 9 and 5 energy. So we can distribute one energy in one particle.
Okay, that is correct. That is the number of way it can be done. I mean,
Yeah.
number of possible distribution. Now, number of ways for number of ways.
Particle 9 to 9 to the power 5.
What you told is correct. That is the distribution. Only one type of distribution. But then each, since these particles are distinguishable, they are like you can separate them. What is the total number of ways this can happen? One possible distribution. That is correct. Because all particles will have the same energy. There
9 to
can
the
be,
power
sorry, there
5.
can be only one quanta per particle. Correct. So wait, there can be one, sorry, one quanta, wait, one quanta, uh, okay, one quanta per particle. Fine. So there are 9 particles and the total energy is 5. So since there can be only one quanta per particle, out of 9 particles, 5 particles will get energy. Remaining 4 will not get energy, right? Okay. See, I have 9 particles. 4, 5, 6, 7, 8, 9. Correct now? So I have how many energy units? 5 energy quantas. Correct. But only one quanta per particle. So I'm giving one. I'll just put E. I'll put E. I'll just distribute one energy part quantas like this. So remaining how many are left out without any energy? 4 are left out, right?
Or yeah.
So, but then in another way, what I can do is I can choose to give energies like this. Fine.
Yeah.
Again, 4 particles will be left out. So now this becomes a question of how many ways you can choose 5 particles out from 9 particles. Got it?
Yeah.
So
9 to the
from
power
9
5 is
you choose 5. That is the idea here. So basically this is again 9 factorial divided by 4 factorial, 5 factorial. So again this is 126. Okay. So now question B. Coming to question B. Now we are assuming that both particles and energy are indistinguishable. So how many ways we can get? Now both are indistinguishable. how many ways we can get? Now n is equal to 9 and r is equal to 5. So since both are indistinguishable, what do we use? What should we use? What should we use? What is it called, Jaydeep? Partition of integer, right?
Yes, sir.
So we use partition of integer. Now we have to choose 5 things from 9. So you can so what we need is, how do you divide 9 particles into 5 ways? So this is what we need to find out now. Okay.
Yes, sir.
So what is the recurrence formula? In sir class taught some recurrence formula, right? What is the recurrence formula? Do you remember the formula?
N factorial divided
No.
by n.
No, 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 no. Recurrence formula for partition of integer. Partition of integer. P of n comma k. What is our teach? P of n comma k is equal to P of, what's the formula? N minus 1 comma k minus 1 plus P of n minus k and k. So this is what's taught in class. So just revise that. This is a general formula that can be used for finding partition of integers. So now we need to find this. So we'll just do this manually. And we can check in Wolfram alpha at the end. So this is n is 9, 5 is k. So how do we do? N minus 1 is what? 8 by 4 plus n minus k. That means 9 minus 5. What is 9 minus 5? 4 comma 5. Anytime you divide a certain number 4 by more than the amount of that number, that is there are 0 ways you can do it. So this is 0. So that now again P8 8 comma 4, you apply this formula, recurrence formula again, and then we do it. Okay, are you following, Jaideep?
Yes, sir.
Okay, plus P4 comma 4. 4 is because 8 minus 4 is 4 and 4. So we have to divide 4 into 4 compartments. So this is 1. There is only one way we can do this. Okay, so this value is 1. So what we'll do is, we'll take that 1 to the front. So we have 1, we have 1 1 array. Okay, we have some problem with my word today. I don't know what. Okay, give me a moment. Just give me a moment. Okay. Okay, seems to be up and running. Okay, so now can you see the screen, Jaideep? Jaideep, can you see the screen? Hello, you there? Can you hear me, Jaideep?
Yes, sir.
So just tell what will come next now. P of what? 7 minus
6
1
comma
is yeah, 6
6
comma
comma
2
2
plus
plus
P of
P 4,3.
4 comma 3. Nice, good. Plus this 1 will come, no?
And
We'll
yeah,
keep doing that. So then what? 5 comma 1 plus P of 4 comma 2 plus again we do this P of 3 comma, we divide this also, 3 comma 2 plus P of 1 comma 3, which is again going to be 0 plus 1. We just, so now this also will be 1 because we are dividing 5 into one partition.
yeah.
Okay,
Um,
so now
as-
this will be 1 plus, now P of 3 comma 1 plus P of 2 comma 2 plus P of 2 comma 1 plus P of 1 comma 2 plus 1. Again this is 0. This will be, all these will be 1. Okay, 1 1 1. So basically now we have how many ones? 1 2 3 4 5. So we have 5. So the value for this now is P 9 comma 5 is 5 ways. So therefore our W value is 5. So these are the number of possible ways we can get, we can arrange 9 distinguishable indistinguishable particles in 5 indistinguishable sites. Okay, right.
yes, sir.
So okay, I'll also show this. I'll what I'll do is I'll show this in Wolfram Alpha. Let's go there. Present something else. Sure. Okay. See this? What I'll do is we are dealing with 9, na? Okay. You see, 9 can be divided into 30 partitions. Now we need to find 9 comma 5. Correct.
Yes, sir.
So 9 comma 5. See, size of partition is 5. So 9 comma 5 is this one. And what is the count there? 5. We also got 5, right? So that is what we are seeing. So you see here 4, 5 is equal to 5. Got it? Do you understand this?
Yes, sir.
Okay. Now we'll press go back. So now this. Again, this is a straight application of formula. You tell me this. Straight application of formula. You tell me this. I think we can just do this quickly. Yes, yes. How many particles? N is 4. How many units of energy? 7. So now you tell me, what is the formula? W total. Same, right? N plus R minus 1 C N minus 1. So what is it? This is 11 minus 1 is 10 C3. Correct. Factorial
Yes, sir.
divided by 7 factorial 3 factorial.
3,
How much is
120.
this? 120. Okay. This is what? 8 into 9 into 10. 2 into 6. Sorry, 3 plus 4 into 3, 120. Correct. So that's all. Simple direct application formula. Not to worry much here. Now you tell me this. quite straightforward. So think about this. We are doing, there are a few things. So with the replacement case, so every time it is 52 cards, and then there are 5 trials, and then we need, okay, oh, sorry, six pulls. There are 6 pulls here. Okay, so this is with replacement. Now you tell me the number of ways it can happen. You have n is equal to 6 tries, and r is equal to 1. Only one, you, because one king only, no, out of 6 pulls. And what are the number of ways this can happen is what they're asking us. So number of ways is equal to, out of 6 tries, you're choosing one king. Fine.
One.
So it's going to be 6 factorial divided by 5 factorial, 1 factorial, which is equal to 6. Fine. Simple.
Yes.
Yeah. Now this question. You tell me how we can do this. You wanted this question, right? Okay. For two boxes and n particles, what is the formula? Sir taught in class, right? 2 boxes and n particles. Correct. So total number of ways, what is the formula? Total possibilities. This is easy. It's like two head or tail and n number of trials. What is the formula there? Both are distinct. 2 power n, na?
Two
Correct?
power.
Huh. So now it's the same thing. Now you extend it. Oh, sorry. Now you extend it to 3 boxes. Instead of 2, we say 3 boxes or 3 particles and n particles. Okay. So now what are the total number of possibilities? Simple, no? You tell. Previously it was 2 power n, now it is
3 to the power n. 3 to the power n.
correct. Simple. Now you take a log of this. Ln of ln w total. What is it?
N 3 to the power n.
And what is that? N will come before n ln 3. Fine.
Yes.
That's all. Simple. Okay.
Okay, sir.
Yeah. So I think that's all. I think I've covered most of the problems. So now let's see if I have missed out any of the questions that you asked. So you asked 2, 5, 5 we did, 7 you asked, and then 9 and 10. Okay. So 9 is quite simple because it's just 25 students and having 2 classmates having the same birthday. It's close to a 0 probability. It's like 1 by 1, 1 by 365 into 1 by 365, which is close to 0. Okay. So then last one, one dimensional lattice multiplicity. This is simple, no? Same. Wait, I'll just show it in this. Wait a minute. I'll explain it. Uh, you see my screen, right?
Yes, sir.
You see, just say, some random question. NA and then NB. So these are the 2 possible sites. Okay, total number of sites is Na plus Nb. So basically, they're asking what are the number of ways this can happen. So here n is equal to Na plus Nb. Fine. And then N1 is equal to Na. And then N2 is equal to Nb. So what we need is, out of this, there are only Na plus Nb, total number of sites. Out of that, in what possible ways can you choose Na? Is something that you can do. So basically, it's going to be like Na plus Nb, choose Na. Okay.
N factorial divided by n1 factorial into n minus
Yeah.
1.
So factorial divided by n1 factorial is Na factorial. So now total is Na plus Nb minus Nb. Sorry, Na plus Nb minus Na. What is left? Na plus Nb, at this right, minus Na. This is what, this is the formula. Directly I'm applying.
NB.
So Na and Na gets cancelled. So it's just going to be like this. Correct? This is the multiplicity.
Yes.
Actually, next week, sir will teach this. This is one of the classical things in statistical mechanics. Okay, you got this point.
Yes, sir.
Okay. So then, one more thing is, no, this seventh question is quite easy. I will not tell you that because it's just a coin toss problem. You have already solved it before. Okay, just see the previous notes. Okay, it's there actually.
Okay, sir.
All right.
Okay, sir.
Do you have any other questions?
No, sir.
Okay, that's it from my side. If you have any other questions, we can discuss. Otherwise, you're free to go. All right.
Okay, sir.
Okay. See you.
Thank you, sir.
Thank you. Bye.